So we have looked at how to design FRR filters by windowing. In this case, we are specifying an ideal response as a boxcar in the frequency domain, and then we're just windowing the time domain representation of that ideal response, basically a sinc function using different kinds of time windows. Right? And and uh, and the target response is basically a boxcar, right? And in Matlab, we have written our own FIR filter based on windowing, right? It's a function that allows us to do this kind of a FIR filter design by windowing, right? That's a function that written by ourselves. Matlab also provides a function for doing similar things, and that function is called FIR1. So if you haven't used FIR1 before, you can just type help FIR1, and it's gonna display the manual page for this particular function. FIR filter design using the window method. You can sort of see how what's actually the purpose for this particular function, right? And its default behavior. Its default behavior is to actually use the Hamming window. Well, the Hamming window is one type of window that we have looked at before, and you also have the option to specify the specific window that you want to use, right? So it's basically saying that nth order FIR filtering using the n+1 length vector WIN to window the impulse response. If this input is empty or omitted, FIR1 is going to use the Hamming window of length n+1, right? That's sort of the default behavior, is to use the Hamming window. But you have the option to specify what this window actually is going to be. You can generate this window by yourself by using those windowing functions that we have looked at before, like a Kaiser, like a Hamming, Henning, right, and all sorts of windowing functions that we have looked at before. Kaiser, right, Kaiser, Chep wing, that kind of thing, right. That's the Matlab function. You can try it, right, and see if it's actually producing different results from our own FIR filters for different kinds of low pass, band pass, and high pass filters, right. That's FIR1, right. It's similar to our own FIR. And then there's another function that's called FIR2. So if you type help FIR2, FIR2 is a FIR filter design by using inverse Fourier transform. So in this case, you don't really have to fix your target or ideal response to be a boxcar. You don't have to. In fact, you can actually specify two input parameters. F is sort of the frequency ranges, and A is sort of the desired amplitude of the filter over each of the frequency point. Basically, these two vectors basically specify a piecewise linear frequency response of the filter, amplitude response of the filter for of any kind of shape. It doesn't have to be a boxcar. You can specify some kind of polynomial, or you can specify some kind of a notch band. It's gonna sort of block out a certain frequency range, right? That kind of a, or it can be sort of band pass or band block, that kind of thing, band stop, that kind of filters by using these two vectors, right? And once you have specified the shape or piecewise linear shape of your desired filter, Matlab is going to sample that piecewise linear function using lots of points, using lots of samples, and that's going to be the sampled frequency domain shape of your desired filter, right? Your ideal response. And then Matlab is going to sort of do an IFFT, do an inverse Fourier transform of those samples, of those sampled frequency domain response, frequency domain representation of your filter, and then convert it back to time domain. And the result is going to be big B. That's going to be your time domain representation of that sampled frequency domain representation of your ideal filter, right? That's FIR2. That's FIR2, right? But you can sort of see FIR2 actually allows you to define an ideal filter that's not exactly a boxcar. You can design a FRR filter with some kind of arbitrary shape, right? So that's something that's kind of desirable. That's something that we would like to have. That's something that we would like um, to utilize, right? So we can actually generalize our filter design by going beyond just windowing a boxcar, windowing the frequency time domain representation of a boxcar, right? So that's called FRR filter design by optimization, right? In this kind of a FRR design by optimization, what we have to do is to sort of kind of optimization means what? Means that I want to minimize the kind of difference between my approximate filter with the desired or target filter, right? So here's the frequency domain representation of our approximate filter, right? And then that's our target filter. Suppose it's a low pass filter, right? That's our target filter. That's a desired filter, right? And then we subtract them and define error. So this error function as a function of frequency is the kind of a difference between the approximate filter and the target filter. We don't really know what this approximate filter yet. We don't know what's actually the exact form of this approximate filter yet. But by minimizing this error, minimizing this kind of deviation, we can determine this approximate filter. And the frequency range for defining this kind of difference is a union of the passband. So it's a low pass, right? So it goes from 0 to omega p, the passband. A union between the passband and the stop band. Right? Omega s is the stop band to pi. So basically, we would like to minimize the deviation between our approximate filter and the target filter within the passband, and also the deviation of the approximate filter and the target filter in the passband. And of course, there's a frequency range that goes from omega p to omega s, which is the transition band, right? But we don't care, right? We don't really care about what's going to happen in the transition band, right? The exact shape of that filter, the approximate filter within this transition band, is sort of not exactly our optimization target. It's not exactly it's not exactly something that we want to control, right? We can leave some sort of frequency band that's unconstrained, for example, right? That's unconstrained. It's in Matlab design, in Matlab functions, it's called do not care region. Those regions that we do not care about, right? So once we have defined this sort of error function, then the purpose of those optimization algorithms is to minimize this error by finding the optimal HA, right? But if you want to minimize this error, we need to sort of define the size of the error. But how do we define the size of the error? It's a function of frequency. It's not just a single number. It's a function of frequency, right? So what's actually the size of a function, right? So there are two different ways for defining the size of the error as a function, right? As the error as a function, right? One is to look at the maximum value of this error function, right? If the maximum error is kind of minimized, then you can imagine that it's conceivable that the entire function, the entire error function as a function of omega frequency is minimized in some sense, right? And if you are using this particular criterion to measure the size of the error, then it's called L infinity norm, or minimax norm, right? And the resulting algorithm has quite a few names, but they all mean more or less the same thing, right? If you see minimax design, then it means that it's actually minimizing the maximum value, the maximum deviation between the approximate and the target, right? And minimax is just one name for it. Sometimes it's called equiripple. It's called equiripple design. So equiripple design is sort of just like a minimax design, because the reason they call it equiripple is because you're actually minimizing the deviations in the pass band and also the stop band. The pass band and the stop band can have ripples. If you actually control the maximum amount of deviation, you're basically controlling the maximum amplitude of those ripples. Right? If you control the maximum amount of ripples, then all the ripples in those passband and stop band will have more or less the same amplitude, and that's why they call it equiripple. Right? And this particular optimization criterion also has a different name called weighted Chebyshev design. Right? And it was because this kind of a criterion was kind of have connections with Chebyshev polynomials, right? And then they got this kind of name. It's called weighted Chebyshev design. And so minimax, equiripple, weighted Chebyshev, all these names actually mean more or less the same thing, right? Maybe not exactly the same, slight deviations, right? Exactly what's actually the algorithm that's being used for doing the optimization could be different, slightly different. Right? But that's a optimization criterion based on the maximum amount of deviation, right? And then there's also another criterion that's called L2 norm, or least squares design. So how do you actually measure the size of the deviation, right? What you do is that you take the energy of the error. Energy of the error is like what? It's like taking the square of the error and then integrate over the frequency band. Integration is basically summation, right? You're basically summing the square of the deviation for every point within your frequency range, and then you minimize this energy of the deviation over the entire frequency range, right? And this kind of criterion is called, this kind of measurement of the size of the function is called the L2 norm. L2 comes from the square. You have to square the error function and then do a summation. That's called L2 norm. And then you minimize that L2 norm, and this technique is called least squares design, right? And Matlab actually provides you a collection of functions for implementing both kinds of approaches, right? And of course, this minimax design or the least squares design actually represents two extreme cases in the entire spectrum of FR filter design, right? You can actually sort of come up with design or optimization technique that actually lies between these two extreme points. And one way of doing that is by introducing a third function. It's called a weighting function, W omega. So basically, you are not exactly the error function. Here, you are defining the error function just as the subtraction, right? The difference between these two functions. But here, you're still subtracting them, but after you subtract them, you multiply with this weighting function. So W omega, also as a function of omega, right? And this weighting function can be designed in specific ways based on your particular application, right? So if you want to emphasize or make the criterion particularly stringent in a particular frequency range, right? You can make the weights in that particular frequency range in a particularly strong, so, right? Give it a big weight, right? But for some regions that you don't really care much, for example, the transition band, or some smaller frequency ranges in the pass band or stop band, you don't care much. You can make the weighting function in that smaller frequency range to be smaller, right? So the area function sort of is not sort of emphasized for that particular sort of frequency range, and then the resulting design, the approximate filter is gonna sort of have larger deviations in those frequency ranges, that kind of thing. And this kind of weighting function is also one of the inputs to some of the Matlab FR filter design functions, right? So now let's look at some of those interesting functions, right? Some of those interesting functions. Matlab actually provides a collection of functions for designing filters based on this minimax or equiripple or weighted Chebyshev principles. This minimizing the maximum value of this deviation function. Two of those functions are kind of most widely used. One of them is called FRPM. And this PM is actually the initial of the two people who actually invented the optimization algorithm. It's kind of a so it's basically telling you it's going to design the optimal equiripple FR filter design. And you can actually specify the shape of the filter that you would like to have in the frequency domain by using these two vectors, big F and big A. So big F is sort of a vector for defining the frequency points at which the amplitude is going to take different values. It's going to be a piecewise linear function. So let's give it a try. And there's another function that's for equiripple design is called FRGR. We're going to look at the FRGR a little bit later, but FRPM and FRGR, both of them are actually widely used. And GR means the generalized limits. I think it's a generalized limits FR filter design. So it's this generalized limits is a particular algorithm for you to optimize or for you to find the optimal approximate HA. So that's the name of the algorithm. It's a minimax filter design algorithm that can be used to design the different types of filters. If type 1 to 4, we're going to explain what's actually types of 1 to 4 linear phase, that kind of thing, in a later video. Minimum phase, that kind of thing, maximum phase. But let's look at the FRPM first, right? Let's look at the FRPM. We're going to reuse our third script S3, right? But we are going to write a new section. So let's try to define what's going to be the target piecewise ideal filter in the frequency domain. So the frequency is going to be the normalized frequency, right? It's the frequency vector that this FRPM function is going to take is a normalized frequency. So Nyquist frequency is 0, right? Nyquist frequency is 1. So we're going to define a few points, 0 frequency, right? And then it's 0.25. And then 0.75, and then 1. That's going to be the frequency points, right? And then our amplitudes of the filter. At 0 frequency, we're going to have a 0 amplitude. At 0.5 frequency, we're still going to have 0 amplitude. So the desired filter that we would like to have is a bandpass filter that has a pass band from 0.25 Hz to 0.25 pi to 0.75 pi, right? But we would like to have so if we define filters like that, then it's still going to be some kind of a boxcar, right? But we would like to have a tapered filter. So instead of just having a jump at these two frequencies, we would like to have a smooth increase. So at 0, it's amplitude 0, but at 0.1, we still have 0, and then at 0.25, it's going to be 1. So from point 1 to point 25, it's going to increase from 0 to 1 linearly, right? And then for the high corner, we're going to do the same thing. Instead of just um, sort of having a sudden jump from unity to 0 amplitudes, we're going to have a linear taper. So 0.9 and then 1. So 0.25 is 1, 0.75 is still 1, right? But at 0.9 you're supposed to drop to 0. So it's 0 here, right? And so that's gonna give us some kind of a tapered boxcar, right? Instead of just a rectangular boxcar. So from 0 to 0.1 hertz, the amplitude is exactly 0. And then from 0.1 to 0.25 hertz, it's gonna increase from 0 to 1. And then from 0.25 to 0.75, it's gonna stay at 1. And then from 0.75 to 0.9, it's gonna drop from 1 to 0. And then from 0.9 to 1, it's gonna stay at 0, right? That's gonna be our target frequency. So now we can call the FRPM function, right? If we don't exactly know how to call it, we can just type help FRPM, and then it's gonna show the usage, how to call it. Basically, the order, basically the number of points you would like to use, the frequency, and then the amplitude, and then the B, the output is gonna have n plus 1 points. It's gonna be a linear phase filter. So you can use it as a in COMV underscore M as a linear phase filter, or call the linear phase filter, or as a zero phase filter. It doesn't really matter too much. So now let's just call it BR. BR equals to no, let's call it BPM, right? BPM equals to FRPM, right? And then let's assume that the number of points is 17 points, and then F, and then A, right? And then if we would like to look at the shape of the function, shape of the function in the frequency domain, then we can use FREQZ, right? And then HW equals to FREQZ, BPM 1. Suppose we would like to have 256 samples in the frequency domain, right? And then we can just make a plot. Let's generate a figure and then make a plot. We're going to plot both the function, both the target, that's FA. Let's use a black line. Let's hold on to this figure, and then also plot the divided by pi, and then ABS big H, right? And then let's use red, right? So that's gonna be our bandpass filter. And you can sort of see the ripples in the passband is kind of more or less the same amplitudes, right? It's not really, and our target is sort of this kind of a piecewise linear, not exactly a boxcar, but a piecewise tapered boxcar, right? And that's for a 17 point or order 17 FRR design, right? And of course, you can actually make it the higher order. For example, if you want to use let's give it some kind of a even number. This is the odd number. Let's give it an even number. Let's use 32, for example, right? 32 points. 32 order, 32nd order, and then let's plot it using a different color, maybe using blue, for example, right? Now I would like to use the old figure, figure 1, still using figure 1. Right. So with more points, you get a better approximation to the target. So red curve is like 17 point, right? 17 point. So and then blue curve is like 32 points, right? So with more points, you can actually get a better approximation to the target. So So that's how you can actually use a bandpass filter. How you can actually design a bandpass FR filter by using the FRPM function, right? And of course, you can also do a low pass filter, right? Let's try to construct another low pass filter, and we're gonna use this low pass filter in later examples. So I'm gonna still write it into a into the script. So I'm gonna call it BR equals to FRPM. I'm gonna use 42 points, and then the frequency is it's gonna be a low pass filter, 37.43, and then 1, and then the amplitude is gonna be 1100. Right, that's gonna give me a low pass filter. And if I want to look at the shape of this particular filter, I can do another HW equals to RQZ, and then BR1 256. Right, and then I can do another figure. Hold on to it. W divided by pi, and then ABS big H. Right, so that's gonna be our low pass filter. Let's just plot it. Right, it's our low pass filter. You can sort of see the ripples. And then we're gonna look at a low pass filter with the same parameters, but just increasing the number of points. I'm gonna sort of do a BR1 equals to FRPM. Instead of 42, I'm gonna use 82. Right, 42, 82. The same kind of frequency and amplitude specifications. I'm gonna copy it over. And then I'm gonna do H1W equals to FREQZ BR1 256. Right. And then I'm gonna plot it on the same figure. It's W divided by pi, and then ABS H1, but using a different color, say red. Right. So if I just execute this section, as expected, the 82 points has a better approximation to the ideal. Right, has a better approximation to the ideal. But now let's compare it. Compare it with FRGR. Right, it's a different function code, but it actually it has some more options. It allows you to sort of specify more options, and then we can compare our filters. Right, so I'm gonna do a BM equals to FRGR. So we can type help FRGR. So it's gonna show us how to use this FRGR function. Right, it's got lots of options, including weights, that kind of thing. And then you also have options about the phase specifications. In this particular case, in this particular example, we're gonna use a minimal phase filter. It's not a linear phase filter, but we're gonna use a minimal phase filter. Right. Well, in a later video, I'm gonna explain what minimal phase actually means. Right. It basically means that both the filter itself and its inverse must have sort of a stable and must be sort of bounded. And usually, in practice, it actually means a minimal group delay. So the group delay is kind of minimized. So FRGR, how do we actually use it? We use it in pretty much the same way, as FRPM. But this time, let's just use 42 points, and then the frequency range and amplitude specifications is similar. I'm gonna copy it over. And then we're gonna specify the weights. We're gonna specify the weights for the passband and the stop band, right? The weights for the passband is gonna be 1. And then for the stop band is 10. So we would like to sort of have the stop band closer to 0, right? That's the higher weights for the stop band. And then we can sort of specify what's actually the phase behavior we want. It's called mean phase, right? And then that's gonna be our BM. Let's call it HMW. BM 256. And then we're still gonna plot HM. And then this time we're gonna use a different color. Let's use green. Right. Still, let's plot it. Evaluate this particular. Can I evaluate this section? So if we look at this particular figure more carefully, the red curve is designed by FRPM, but with 82 points, right? Both the blue curve and the green curve were designed using just 42 points, right? Using just 42 points, and green curve was designed by using FIRGR, and blue curve is designed by FRPM, right? And for the green curve, you can sort of see the stop band has a smaller amplitudes than the blue curve, right? Because we have a higher weights for the stop band, right? We want the stop band to be close to the target, right? In the passband, the amplitude repose is kind of similar. The amplitude is about the same. It's not really differing too much. It's slightly smaller, right? But it's not really as small as the red curve, right? It's not exactly as small as the red curve, right? That the reason is that it's a minimal phase. Minimal phase, you actually relaxing the requirement for the phase, basically, right? It's not exactly a 0 phase, so you actually allow the phase to have some value, right? To have some kind of a non-ideal value, right? If you have 0 phase or linear phase, that might be sort of more desirable, but minimal phase has a non-zero phase, but it's still minimal, right? So the group delay is like minimized. So you're actually sort of relaxing the requirement on phase, so you get better behavior. You get slightly better behavior in the passband, right? And that's two of the functions that's kind of widely used for equiripple filters or minimax design, right? But let's also look at the least squares design, right? And Matlab also provides another function that's called FIRLS. It's called FIRLS. So we're gonna do another filter that's called BLS equals to FIRLS. Right, and for this FRLS, we're still gonna use 42 points, and then the frequency and amplitude specification is the same. Right. This is the same kind of target frequency, basically. Target frequency behavior. Right. And then we're gonna do big H ALS, big W equals to FREQZ, BLS 256. Right. And then we're gonna plot it. But with again with a different color. Let's just use black. We haven't used black before. Right. And then let's just execute this section and see what's gonna happen. All right, that's gonna. So let's try to blow up this passband and see what's going to be the behavior of the passband. Right. So the black line is sort of the ripple in the passband generated by the FRAoS, the least square criterion. If you look at the least square criterion, you can sort of see right away what's actually the difference. Right, the ripple size is like different. It's kind of different, and it has a bigger amplitudes at the boundary of the stop band of the passband. Right, the ripple actually has a maximum amplitude here, close to the boundary of the passband, and the amplitude of the ripples actually it's not really more or less the same for the equiripple design. It's actually the amplitude of the ripples is actually smaller at the beginning, and then gets bigger and bigger, right? But the total amount of energy of those deviation from the target, which should be flat exactly equal to 1, is minimized for this particular design, right? And you can also look at the stop band, right? The stop band for the equiripple design, the amplitude of the ripples is more or less the same. But for the black curve, which is the least square design, you can sort of see the ripple is biggest close to the boundary of the stop band, right? That's the so that's the black curve here, right? And then it gets smaller and smaller, right? So that's kind of the behavior of using a least square design and using a equiripple design. That's the kind of differences, right? And Matlab also provides another least square design function called FAoS, FRCAoS, constrained least square, right? And if you look at its manual page, so that's the order of the filter, and then frequency, and then amplitude, and then it also allows you to specify 2 more vectors as input, which is actually the upper and lower bounds of the deviations from the target. So you can actually constrain the least square optimization to allow just a maximum amount of deviations for the and the lower and the lower bounds of the deviations. So give the deviations some kind of a boundary. So the optimized filter is going to have the approximate filter is going to have some kind of deviations that's going to be bounded by this particular range, right? And it has some examples to show you how to use those boundaries. And but let's look at one more thing. We are going to look at the time domain representation of BR and BM. The time domain representation of that low pass filter generated by FRPM and the low pass filter generated by FRGR. It's called BR and BM. Let's just make another plot. Let's just generate another figure. Let's just generate another figure, and then maybe hold on to it. Let's make a horizontal axis, so n goes from 0 like 42, so 43 points, and then it's just a plot AMBR. Let's use blue circles, and then plot AMBM. Let's use red star connected by lines, right? And then let's just make a plot. So these are the 2 functions that actually represents the 42 points filters or FR filters designed by these 2 different functions, FRPM and FRGR. For the FRGR function, for the FRPM function, it's still linear phase. It's still linear phase, so you can sort of see it's symmetric. It's a symmetric function with a non-zero amount of shift, right? It's a symmetric. And the amount of shift is like 21 or something, right? Close to 21, right? That's a linear phase filter. But for FRGR, it's not a linear phase filter anymore. It's a minimal phase. It's a mini phase. And then you can sort of see the difference between a linear phase filter and a minimal phase filter. For a minimal phase filter, it's certainly not. It's not a a symmetric function anymore, right? It's not a symmetric filter anymore, right? But you can sort of see most of the amplitudes, the big amplitudes, are kind of clustered close to 0. It's actually a kind of a typical behavior for minimal phase filters. It has minimal group delay. We're gonna talk about what group delay actually means, right? And this kind of behavior, well, it's caudal. It's still caudal, but it's gonna minimize the kind of distortions in the shape of the waveforms, right? Uh, so if we would like to filter some kind of input signal with these two filters, we can just use our C1V underscore M function, just like before, right? Just like what we did uh, in in this particular example, right? So let's try to um, define our input signal. Let's just copy over these two lines, right? That's our input signal, some kind of second order derivative of a Gaussian, I think, and then let's paste it over here, and then we can just filter them, filter this input signal using BR or BM, right? And um, so let's just do y, and y equals to C1V underscore M x bx br. It's gonna require a horizontal axis. Let's just assume it's going from 0 to like 42, right? How many points we are using? It's I have a variable here. It's n, right? So I can just use n here, right? Um, let's let's generate a new figure and then hold on to it, and then we can just plot ny. Right, this is sort of in blue, and then y and y equals to C1V underscore M x, no, not bx, no, it's s, right? S bm, and then n, right? And then plot ny y, and using some other color, right? And then we can just maybe put it into a different section. No, nx, no, I think s and x, right? It's supposed to be s and x. Maybe we should also put the original signal on top of it. XS, and then let's use black for the original signal without the filter, right? So now let's look closely at the changes in the shape of the waveforms. Right? Maybe we should just blow up the center section. Xlim goes from like a 400 to 600, I think. So now you sort of see the kind of differences for different kinds of filters, right? And so the black curve was the original second order derivative, right? Gaussian, second order derivative of Gaussian. And then the blue curve was generated by using FRPM, and it's a symmetric linear phase caudal filter, right? And then the red curve is for the FRGR filter, right? BM, I think. FRGR filter. It's a minimal phase, right? So you can sort of see the difference between a linear phase and a minimal phase. Linear phase doesn't change the shape of the waveform too much. There are still deviations to the original waveform because you have applied a filter on it. But you can sort of see it's still symmetric. But for the minimal phase filter, it's not, right? You can sort of see the waveform is no longer symmetric anymore, right? And in addition to the changes in the shape, you can also see amplitudes has been sort of are different. But you can see that the deviation, the shift is kind of a minimal, right? The group delay is actually kind of minimal. It's not really like the linear phase thing that has been shifted by a huge amount. It's still, so if you are seismologist, you care about the onset time of the first break, right? Of the first break. So so for this raw signal, it has a negative polarity, right? It has a negative polarity, and the onset time is at about this location. And then if you actually look at the minimal phase filter, the red curve, the onset time is still about the same, right? It's not really changing too much, right? It's not really changing too much, and the polarity is still the same as negative, right? The signal is actually having a negative amplitude polarity. But for the minimal phase, for the linear phase filter, the amount of shift is like a lot bigger, right? So it actually, if you actually trying to pick the first arrival time, the linear phase filter could give you a wrong pick. You might want to pick at somewhere here, right? If you're actually using a linear phase filter. But for a minimal phase filter, the pick is probably the same as the raw signal, right? It's not deviating too much. So that's one example about the different kind of the effects of different kind of phases, and also the FIRGR and FRPM function calls for you to construct those FIR filters.